In the previous examples, we converted a set of discrete forces and moments, that is, force couples, into a single resultant force and resultant moment at a specific location. We now want to take this one step further, reducing the equivalent load system to its simplest possible form. In many cases, it will be possible to reduce the equivalent load system to just a single resultant force. In the most general three-dimensional case, it is possible to reduce the equivalent load system to a single resultant force and a collinear resultant moment. This latter combination is referred to as a wrench, but the collinear pushing and twisting make it more analogous to the loads applied when using a screwdriver. We begin by discussing some special force systems, the concurrent, coplanar, and parallel force systems. These will all be reducible to a single resultant force. A force system is said to be concurrent if the lines of action of all the forces intersect at a common point. We can see that if we find the resultant moment of these forces about their point of intersection, the resultant moment is zero, since there are no moment arms for any of the forces. The force system is then reducible to a single resultant force acting at the point of intersection of the lines of action. The second special force system is the coplanar force system. This is a system in which all the forces lie in the same plane and all moments are perpendicular to that plane. Note that all two-dimensional problems are, by definition, coplanar force systems, typically all forces in the xy plane and all moments in the z direction. The first step in finding the equivalent force system for this class of problem is picking some reference point, A in figure B, and finding the resultant force and moment at that location. We did that in our previous examples. The second step is asking if we can simplify this force system further by shifting the line of action of the resultant force so that it produces the same resultant moment about point A as in figure C. Note that the lines of action of the resultant force and resultant moment are perpendicular to each other, so we have a mutually orthogonal coordinate system between these two lines and a third line perpendicular to both of the first two. We then need to ask, in order to produce the desired resultant moment, do I need to shift the resultant force into the foreground or into the background? The easiest way to test this is with the right-hand rule, where we cross R into F and let our thumb tell us the direction of the corresponding moment. If we do this in figure C, we see that in fact we need to shift the resultant force into the foreground so that its moment about A has the same sense as the resultant moment calculated in figure B. Note also in figure C that we are effectively using the scalar approach to find the magnitude of the shift in D equals the ratio of the moment magnitude to the resultant force magnitude. Our final answer is that the single resultant force applied at point B is equivalent to the set of loads shown initially in figure A. The last special force system is the parallel force system. This is similar to the coplanar force system with the directions of forces and moments reversed. Here the forces are all in one direction, let's say the z direction, and all the moments lie in the xy plane. Again, the first step is to pick a reference point somewhere on the body and to find the resultant force and moment at that location. Again, the lines of action of resultant force and moment are perpendicular, so it's possible to shift the line of action of the resultant force to a second location, point B in figure C. And finally, the direction of the shift is determined by the right-hand rule, and the magnitude of the shift can be calculated relatively easily using the scalar approach. So this figure shows our shift in the resultant force as being from A to B. If I just slide this position vector out a little further and use the right-hand rule to take the cross, we'll see that we do in fact get a resultant moment in the correct direction. So we need to shift it from A towards B in the direction shown into the background now rather than into the foreground. And again, we've used the scalar approach to find the magnitude of that shift as the ratio of the magnitude of the resultant moment to the magnitude of the resultant force. The final special force system is the wrench. This is not so much a special system as the general representation of the simplest reducible form of any arbitrary combination of loads. We begin as before by picking a reference point A and finding the resultant force and resultant moment at that location. Because an arbitrary set of loads is not special in any way, there is no guarantee that the resultant moment will be perpendicular to the resultant force, as was the case with the coplanar and parallel force systems. So we begin by resolving the resultant moment into components parallel and perpendicular to the resultant force. We can write m parallel vector as having a magnitude equal to the projection of the resultant moment on the direction of the resultant force. We would write that as mr dotted into a unit vector that points in the direction of f. That's a magnitude, and because it is parallel to the resultant force, we put that on the unit vector pointing in the direction of the force. We then define the perpendicular moment as the difference between the resultant moment and the parallel component. Now treat the combination of resultant force and perpendicular resultant moment the same way we treated the resultant force resultant moment combination in the coplanar or parallel force system. We shift the resultant force to a new location, B in figure C, so that the moment produced by the resultant force matches the perpendicular component. And again, we have our position vector from A to B. If I slide that again along this direction and take the cross R cross F, that will give me the perpendicular moment component that we can see in figure B. We are left with the resultant force and the parallel moment component. The coaxial nature of this load pair is the kind of collinear pushing and twisting you would apply if you were using a screwdriver on a fastener. So even though the name of this force system is a wrench, it really is more appropriate to think about it as a kind of action that would accompany the use of a screwdriver. One additional comment about the shift in figure C. The figure suggests a scalar approach can be used to find the magnitude of the shift. But because this representation occurs in arbitrary, three-dimensional problems, it is often impractical to use the scalar approach to find the magnitude of the shift. Instead, a vector approach is needed. We'll get a better feel for this when we look at an example. To begin, though, we'll look at an example involving a coplanar force system. In this third example, we have three loads applied to a tiered column. We want to determine the equivalent force system at B, and then determine where to shift the resultant force along the column so that we can replace the resultant force, resultant moment at B with just the resultant force. The resultant force is just the vector sum of the two forces shown in the figure. Given the 3, 4, 5 triangle orientation accompanying the 900 Newton force at B, we can write the resultant force as 600 plus 4/5 900 newtons in I minus 3/5 of 900 newtons in J. This gives us a result of 1320 I minus 540 J newtons. For the resultant moment, note first that the 900 Newton force contributes nothing since its line of action goes through B. The 1000 Newton meter moment, that is, the force couple, has the same influence everywhere on the body, so it also contributes to B. The 600 Newton force at D contributes a 2400 Newton meter moment in the same direction as the force couple. They're both clockwise, so we end up with a resultant moment at B that's equal to minus 3400 K Newton meters. To determine the location for shifting the resultant force so that we can eliminate the moment, there are a couple of ways we could proceed. Now, if I wanted to find a orientation perpendicular to both the resultant force and the resultant moment, here's my shifted line of action of the resultant force. I would use my scalar approach to find this distance, and then somehow I'd have to come back here to find where the force intersects the tiered column. As an alternative to that, we can do something a little bit different. We can note that our resultant force has two components. It has a y component and an x component. And the y component doesn't contribute anything to the moment about B. So instead, let me just focus on the x component and ask where I should shift this so that I get the same moment about B as I've just calculated for my resultant moment. And I can see that I'm going to need to shift this above B, because then the combination of this moment arm and this x component force will also give me a clockwise moment that will match the 3,400 Newton meter moment that I have here. So now what I'm going to do is I'm going to calculate a displacement in y. It's a little bit different than the shift that we talked about earlier, which was just the resultant moment over the resultant force. This is the shift in y, which will be the resultant moment magnitude over the x component of the resultant force, which is the only one that contributes anything to the resultant moment about B. So this is 3,400 Newton meters over 1,320 newtons, and that gives me a value that's equal to 2.576 meters. Now the problem asks for the y-coordinate of the point where its line of action intersects the y-axis, so we have to add 2 meters onto that, and that would be 2 plus dy, which would be 4.576 meters. Finally, we take a look at a problem where we need to turn a set of discrete forces into a wrench force system. Our first step involves selecting a point to establish an equivalent force system. We have not been told what to choose, so we'll look at two different possibilities and see what changes and what stays the same as we work through the details. Before we start, let's just summarize some steps that we're going to need to perform this operation. First, we're going to pick a reference point for our first step of establishing an equivalent force system. So I'm going to say pick a reference point O. Then we're going to find our equivalent force system at O, our resultant force and our resultant moment about O. Then we're going to resolve that resultant moment into parallel and perpendicular components, where the parallel component is aligned with the line of action of the resultant force. And then finally, we're going to calculate the shift to reduce this to a wrench. Now, something that will be different here is we're really going to need to use a vector approach to calculate this shift rather than a scalar approach. And we'll see what that entails when we get that far. Okay, but keep in mind these steps as we work through a problem. So again, one of the things that's a little bit confusing or intimidating about this particular problem is it has not provided the reference point. It simply asks us to find the point P where the line of action of this force intersects the plate. So it has kind of bypassed the first step of the problem in the problem statement. So I'm going to choose, for a first solution, I'm going to choose our reference point O to be A. Now, again, this problem is at least relatively straightforward in the sense that we have these three force components and they all act in a different direction, so that at least the resultant force is a relatively easy thing to find. We can see that it's just going to be 500I plus 300J plus 800k newtons. Okay, and if we take the square root of the sum of the squares, this is not one that works out so cleanly, but the resultant here is very close to exactly 990 newtons. It's actually something like 989.95, but we'll just use 990 for our resultant force. And if we want to know the resultant moment about A, we could use either the scalar approach or the vector approach. The scalar approach works very nicely here because, again, we have the forces that are aligned with different coordinate axes, and we can see things very clearly. The force at A will contribute nothing because its line of action goes through A. If we look at the contribution from the force at B, it acts in the z direction. The position vector from A to B is aligned with y. So if we take a j and we cross it into a k, we're going to get a result that's in the I direction. And so here we're going to have 4 meters times 800 newtons is 3,200 newton meters, and that's going to act in the I direction. So from the scalar approach, that contribution is 3,200 I newton meters. And then if we take a look at the contribution from C, we have this position vector, we're crossing it into this force vector, and we've got something along I crossed into something along J, and that's going to give us a result in the K direction. So we have 6 meters times 300 newtons. It's going to be 1,800 newton meters, and it's going to be in the K direction. So our resultant moment about A has these two components. Okay, so that's step one. Our next step then is to resolve the resultant moment into components parallel and perpendicular to the resultant force. So I can define a unit vector that points along the direction of the force, and those components end up being equal to 0.505I plus 0.303J plus 0.808K. The magnitude of the parallel component is the dot product between that unit vector and the resultant moment at A. And so we have no J component for the resultant moment of A. This ends up being 0.505 times 3,200 plus 0.808 times 1,800, and that gives us a value that's equal to 3070 newton meters. So our M parallel vector is 3070 newton meters on the unit vector that points in the direction of F, and that ends up being equal to 1550I plus 930J plus 2480K newton meters. We can then find the perpendicular component as the difference between the resultant moment at A and M parallel, and those components are equal to 1650I minus 930J minus 680K newton meters. Our final step is the calculation of the shift. And before we go through those details, I'm going to just come right back up to our figure for a second and now talk about why this is going to be a little bit more complicated and why we're going to have to use a vector approach. So the first thing we can do is we can kind of sketch qualitatively where the resultant force and moment components are going to look like within this three-dimensional space. We have there are positive values for all force components. So if I were to try to represent the resultant force and the parallel moment in this space, it's in the octant of three-dimensional space where x, y, and z are all positive. So this is my attempt to make my force vector come out at me from the screen, and the corresponding parallel moment component would be here. So here's our resultant force, and here's our parallel moment. And then if you look at the components of the perpendicular moment, that's positive in I, negative in J, and negative in K. So here's my attempt to represent that. Here is our perpendicular. So you have to imagine this is coming out at X, but going backwards in Y and going down a little bit in Z. And so the idea here is we want to know where to shift this resultant force so that this RAP crossed into the resultant force will produce this perpendicular moment. So if I've represented this correctly, MR perp is going to be perpendicular to both RAP and FR because it's formed from the cross product of RAP and FR. So with that in mind, I'm going to come back down to the bottom here and note that RAP in this coordinate system is X units in I plus Y units in J. I don't know where it is. These are my unknowns. And then the shift in the form of the vector approach looks like this. I want to find X and Y such that RAP cross the resultant force is that perpendicular moment. So what does this look like? So the cross product on the left-hand side has these components. I'm looking for X and Y. And that has to match a perpendicular moment that I know. So that's got to be equal to 1650I minus 930J minus 680K Newton meters. Now, one of the things that makes this a little bit unsettling is that we're going to get 3 scalar component equations out of this, but we have just 2 unknowns. And if we've done this problem correctly, what we should be able to do is pick any 2 of those 3 scalar equations and solve for X and Y and just use the third one to verify that we have a self-consistent solution. So in the I direction, the scalar component of I from the left-hand side, we have 800 times Y. That has to match the 1650. And in J, on the left-hand side, we have minus 800x. That has to match the minus 930. And in K, we have 300x minus 500y, and that has to match the minus 680. So you can choose any 2 of these equations you like. If you choose these first 2, you get y equals 2.06 meters and x equals 1.16 meters. And then if you go back and plug those results into this final equation, you should be able to verify that the left and right-hand sides are the same to within the round-off errors that we've incurred as we've been doing our calculations. So now let's pick a different reference point. In my second solution, I'm going to choose B as my reference point. So what's going to change here between this and solution 1? I'm going to have the same resultant force. That hasn't changed. I am going to get a different resultant moment now about B, because you'll notice that my moment arms to these forces are here respectively, and both of those cross products are going to produce results in the plus Z direction. So I get no contribution from the force that goes through B. For FA, I'm going to have 4 meters times 500 newtons, and the result of that cross is going to be in the plus K direction. It's going to give me 2,000 newton meters in K. And then again, I'm going to have a 6 meters times 300 newtons, 1,800 newton meters, also in K. So now, if I go back and start over, for solution 2, we're going to make point B the reference point. And our resultant force and the corresponding unit vector are the same. Okay, but now our resultant moment about B is going to be different. This is going to be 3,800 K Newton meters. But if we go now and find M parallel as the dot product of the unit vector with the resultant moment about B, that is 0.808 times 3,800, and that is also 3070 Newton meters. So that's the same. The resultant force and the parallel component of resultant moment are the same. That's encouraging because we don't want to get a different pair depending on our reference point. So our M parallel vector is still 3070 on the unit vector that points in the direction of the force, and that's unchanged. But now, because the resultant moment at B is different, the perpendicular moment will also be different. MRB is different from MRA. M parallel is the same, so this will be different. And in this case, it's minus 1550 I minus 930 J plus 1320 K Newton meters. Okay, so now again, before we continue, I'm going to come back up here. Once again, I'm going to sketch that location at B now. I've got my resultant force coming up like this, corresponding parallel component of the moment looks like this. And notice that my perpendicular moment now is negative in I and J, but positive in K. And so that is going to have relatively this orientation in this figure. And now what I want to know is where to shift this pair combination from B to P so that the cross product between RBP and the resultant force produces this resultant moment. And so again, if I've drawn this well, that should be perpendicular to both of these. Okay, so note that the representation of RBP in this case goes from B to P, and so RBP will not look like RAP. But I should get the same X and Y no matter how I do this. So now I'll come all the way back down to the bottom, and we'll note that RBP is RP minus RB, and that will be XI minus quantity 4 minus YJ. Again, we want to find X and Y such that RBP cross the resultant force is equal to the perpendicular moment. That looks like this, which is now equal to minus 1550I minus 930J plus 1320K Newton meters. And if we write those individual scalar components, we have minus 800 times 4 minus y has to equal minus 1550. In J, we have minus 800x equals minus 930. And in K, we have 300x plus 4 minus y times 500 equals 1320. Again, we can use any two of these three. If we use the first two, we get again y is equal to 2.06 meters and x is equal to 1.16 meters. And we can verify from the last equation that the left-hand and right-hand sides are consistent. I realize this was a long exercise, but the point is that the equivalent force system in 3 dimensions is probably best calculated using the vector approach for the shift, and that it doesn't matter what you pick for your initial reference point, as long as you're consistent in doing the calculations, you should find that the location of that resultant force parallel moment pair ends up at the same location.